Okay, so right here, the number of kilocalories we're looking at. So right here, again, these were those moderate activity, high activity kcals that you could take in, or capital C calories. These are for the different age categories. As we get older, we get less active usually, and our bodies tend to use up less calories overall. Our metabolism just slows down a bit. Okay? But there you go. Anybody have any questions about that so far? Okay. These are the energy uses of different activities, by the way. And so, for example, if I sit all the time, and that's the big activity I do, sit and lecture, right? I'm only using a little bit more than 100 kcal per hour. And that's going to be really tough for me to burn my calories per day, right? Yeah. Walking, on the other hand, when I pace around in my office and labs, it helps a little, but not as much as I'd like, right? Okay. I need to start doing things like swimming or running. So what needs to happen is everybody needs to start lighting themselves on fire in lab, so I have to run everywhere, right? That's Dr. Clausen's exercise plan, huh? Okay. So specific heat. This is going to be different for different substances. It's going to be the amount of heat that's needed to raise the temperature exactly 1 gram of substance by exactly 1 degree Celsius. It has units of joules per gram degree Celsius. Both those terms are on the bottom, by the way. And the SI system, that's for the SI system. The metric system has calories per gram degree Celsius. Big difference being calories versus joules, right? So again, this is the formula for specific heat. It's heat over mass and change temperature. You can actually get that from the units right here. So this right here is energy, isn't it? Or heat in this case. This right here is mass. And that right here is change in temperature. Okay? Okay. This is actually the specific heat for liquid water right there. And so if you ever went into a pool on a hot day and the pool is not as hot as the surrounding temperature, it's a little cooler. Why would that be? Or has anybody ever been to like the north coast? Okay. And so when you get into the water on the north coast, they're always a bit cold, right? Okay. Why would that be?
Because the specific heat of water is higher than a air.
Exactly. It takes time to warm it up, right? And that time is the specific heat right here. Okay. Why do you use metal for pans? Gets hot faster. Why do you use like a cloth or rubber for the grip? Doesn't get hot as fast. Exactly. And so it doesn't transmit that heat as fast. What would happen if you just sat there and held it with a cloth? Yeah, eventually it would warm up, right? And you could eventually light it on fire if it's hot enough in that point. Okay? It would be a very bad idea, but it would happen. So why do they use things like copper and aluminum for things that need to transfer heat quickly? Because they can propagate the heat quickly, right? They warm up pretty fast, and then they can move that temperature to the air fast if you put air across it. Okay? Specifically, aluminum does a really good job of that. But anyways, this is water right here. It's probably the most important specific heat. So if you're going to memorize any specific heat, that would be the one to do it, or have it written down somewhere. It is the definition for specific heat. Anybody realize that? That's the definition of the calorie, isn't it? 1 calorie raises 1 gram of water 1 degree Celsius. That's why that does that. That's the specific heat of water. Okay? And so that's the universal constant that actually sets calories. It was always specific heat. Okay? And notice the 4.184, that's the conversion factor between calories and joules, because all you're doing is converting calories here. Okay? All right, so what is the specific heat if 24.8 grams of metal absorbs 274 joules of energy and the temperature rises, from 20.2 degrees Celsius to 24.5 degrees Celsius? Okay, so what was specific heat again?
The amount of energy needed to raise 1 gram of something 1 degree Celsius.
You got it. So we do joules on top, right? So that's the amount of energy. It's going to raise the temperature of a gram 1 degree Celsius, right? Okay, so we need to do this. There's two different ways you can think about this. You could use a formula for this. You'd have to memorize or have the formula in your head somehow. Alternatively, you can actually just use dimensional analysis, i.e. cancel out units until you get the correct units. Okay, I'm going to show you in my writing here the way to do it with dimensional analysis. And then the book always does everything formulaic, okay? And the reason for that is people feel like it's easier to teach. Unfortunately, it also means you become almost useless to do anything. So, like, and you get out of the real world, there's not a genie that's popping in on your shoulder and going, the formula for this one is, I'm going to set up a problem that will use the formula here. Like, in the real world, there's a million formulas. You never know which one you're going to need, right? Okay. So, what can we do? Well, we can actually substitute these in so we would have the correct units each place, right? So what's going to end up being on top? Yep, 275 joules. You got it. Okay. And then what's going to end up being on bottom? Yep, 24.8 grams, right? Does it actually matter exactly what metal we are to figure this out? Nah, it doesn't really matter, does it? Okay. Did everybody notice that I was actually doing what do I have, what I need, how do I get there? I just stopped actually saying that. Okay. All right. So how do we get the degrees Celsius number? Do I just take one of these? Yeah, I need the difference, exactly. What if I mess up? Like, which one do I do? Which one's the positive? Which one's the negative? Yeah. So technically, I could do final minus initial, which is how you do changes, right? And so I end here, the 24, and I start here. The other thing I could realize is that when I'm talking about heat, all a positive and negative is the direction. And in this case, I don't care what the direction is, do I? All I care is how easily this moves the temperature. Okay? So whatever I get out, positive or negative, it doesn't matter. I just take the number as if I ignored that. Okay? Or I do the absolute value. That's another way of saying that. Okay. And so it doesn't actually matter if you do this the correct way, but I'm going to do it the correct way. Just, wow. That was, you're kidding me. Okay, I'm going to do it the correct way real quick. 24.5 minus 20.2 degrees Celsius. And that difference is 4.3. Fantastic. And everybody did that quickly without having to use a calculator, which is also pretty good. Good deal. All right. So we're going to go to 75 again, because it got rid of that, divided by the 24.8 grams, and then on the bottom still 4.3 degrees Celsius, right? Did I just lose the projector?
It'll take a minute.
Okay. Wow. I really don't know what's going on with that. This wire here is like cursed or something. Yeah. Okay, anyways, I just go ahead and do that in my calculator now, right? Okay, so this right here divided by that one, and then the number you get out, you can divide it by that one, right? Fantastic. Anybody have any questions? Did I lose anybody in any way whatsoever? Nope. Excellent. Okay, so this is the formulaic way of doing it. You can express each of these. And so again, what I have, what I need, how do I get there? And so then I would do the change in temperature separately, just like I did before. And then I'd have the formula and I would substitute it in, right? Now, the problem with this, you need all the formulas. And so you either have to have a cheat sheet, which you will be able to use, yes. You can have notes during the exam. I would not just try to bring your notebook, because you will not have time to look up every single, through like 20, 30 pages of stuff, okay, for every single problem. But you will want to condense your notes to some degree, okay, or have some way of quickly getting to stuff. You can also have a scrap paper, scientific calculator, yeah, no computer device at all. Make sure the calculator is not your phone. Okay, so then you would substitute each of these in on the formula. What's our number of sig figs, by the way? 2, exactly. And that's because of this bottom one right here, right? Mm-hmm.
What would that new unit be called that's on the denominator? Like, it says grams, degrees Celsius, but like, how do you say that?
Joules, grams, degrees Celsius.
That's it.
Joules per gram, degrees Celsius. Yeah.
How would you enter that in a percent?
So what you would do is there's 2 ways you should be able to enter it. The way that will work for sure is, you know how the Pearson has that little tool that is box over box? Okay. You put one of those, and on top of the box you can put your number and then joules. The bottom of the box is going to be grams, degrees Celsius.
I did it.
Mhm.
I never put it like that. Like, I always just did joules and then said it was grams.
Really?
Normally it just had that on the side. But I only
Yes.
have 2 questions left, but so far it's just had it to the side. I haven't had to like type that.
Yeah, there are a few questions Pearson does, usually to test out your understanding of like formulas. But overall, Pearson does not have these more complex units where you have to enter. That's pretty unusual, especially for this class.
So like test day, we're going, it's joules over.
It's a multiple choice exam with a, yeah,
Is it really?
yeah,
Oh my buckets.
yeah. And it's a Scantron. Yeah.
How many questions are we gonna be?
Yeah, there's no way I can depend on the internet to do an online exam or something. And, yeah.
And it's just multiple choice?
Yeah. The number of questions is kind of a difficult question for me to answer. I do things by time. So the exam is a 45-minute to 50-minute for the average taker. Okay? Quick people will get it done in 20-something minutes. Slow people will need the whole hour.
Is that
Okay.
like Pearson time, or is Pearson time be saying 45 minutes and then it's like an hour and a half?
So these first homeworks, they are an hour and a half sort of stuff. Starting the next chapter, because people had already started on 3, so I couldn't remove questions. I can't do anything. Starting the next chapter, it is a 50-minute to an hour for the homeworks. Now again, that is the average time over, let's see, most questions have somewhere between 6,000 and 8,000 students that have taken them. So that's the average time. But almost nobody is the average time, right? No. So some people are getting them done in like, I've had people get these things done in 15 and 20 minutes. And some people get them done in an hour, hour and a half. So, yeah. The difference in human ability, have you guys ever heard of the Pareto effect? Yeah, so it's called the Pareto effect. And essentially, if you take the square root of any given population, those people will produce 50% of the output in anything. So like 1 out of 10 people would produce 50% of the hit songs, would produce 50% of the inventions in a field. And vice versa also happens. And so humans are ridiculously variable. Like the strongest person on the planet is 10 times stronger than me. And the weakest person on the planet is over 10 times weaker than me. And
So basically you're so strong.
yeah, I'm somewhere in the average ish. So, yeah, when you see an average number, please remember that average numbers for humans are totally almost meaningless, and we have these huge tails
Yeah, 'cause
both
there's
directions.
like 35 to 40 minutes, and then it's like 2 hours later.
Yeah. And honestly, the worst times are going to be these first homeworks, because you're trying to get into the chemistry and learn those things. Like these first 2 homeworks, by state and federal law, the middle schools actually should have taught that.
I just don't think Pearson explains it very well.
No, that's fair, actually. I'm not a huge fan of Pearson or this book in general. And there's a lot of the questions that I probably would not have asked him like that, but you guys bought this, and I don't want to waste the resource, and having instantaneous feedback on questions is more valuable than not, right? So it is the tool I have to give you, and it's more useful than nothing.
Is it a tool or is it a hindrance?
It's a tool, yeah, because you do need practice prompts. And having the instantaneous feedback on the practice prompts is helpful. So, yeah. Don't like Pearson. If you ever get a chance, there's a program called SmartWorks. Norton has it. That one's much better.
I just go watch YouTube videos.
That's fair. That's fair. Or ask me.
I did once.
Hmm?
That's what I did once.
You did once.
One time I asked.
Don't want to ask again?
No, I got a little scared.
Oh, okay. Well, sorry, scared you off. I didn't. Am I really that scary?
Maybe a little.
I have an evil laugh.
It's some gang fights. They got me.
Oh, okay, okay. I haven't been part of a violent activity in like 20 years
No,
almost.
I just want to ask, and you'd be like, "Oh, that's stupid."
Oh, no, no, no. There is no stupid question on chemistry. Like, even what is a question is not a stupid question. Like, chemistry is just not like most of the other classes. Please, if you guys have any questions, do not actually be afraid of appearing stupid. And honestly, there's probably other people with that same question, and they're like you, afraid to ask. Like, so. And the questions that come up every time are a little bit different. So anyways. All right, anyways, here's some different specific heats for different substances. For example, let's say I wanted to make something that's a heat exchanger for something that produces a lot of heat, and it's very important it stays cool so it can continue doing its job. What would I use? Like a CPU in your computer.
You're asking the wrong person.
Yeah, so most of the times you're going to see it made out of copper. And could I make it better?
Yeah.
Yeah. How about gold? Is that better? Yeah, it is. And it's more expensive. Well, a lot more expensive. And so people that go really crazy for computer stuff actually will take gold coins and file them down and use those. Yeah. You can buy gold coins.
Really?
Oh yeah.
Have you not seen the commercials for the people that like?
Oh yeah.
Roslyn Gold.
Oh, yeah, because I was buying gold coins instead of buying
Yeah, they're
stocks or
like,
something.
the economy today is so scary. You should buy
Yeah,
Roslyn Gold.
I find it so funny. And almost all of those things, they're storing it in some vault like 2,000, 4,000 miles away from you. All right, so let's talk a bit about specific heat of the water. The high specific heat of your water and the large mass of your water is the reason coastal cities don't get crazy temperature changes. If you look at the Midwest, has everybody seen the Midwest weather reports? So on the worst days of summer, they'll actually get worse than the Sahara Desert. On the worst days of winter, they actually get worse than some of the Arctic regions, like Siberia. And it's because there's no large bodies of water, right? And so whatever the temperature, yeah, it slides down really far and it slides up really far. Okay. On the other hand, if you have a lot of water bodies, those water bodies will resist their temperature changes, and so they're going to modulate your temperatures. And so overall, your temperatures are much more even, less extreme. The averages are about the same, though, given their equatorial lineup. So when ocean water cools, the surrounding air does what? So sand in the desert is hot in the day and cool at night. Sand must have a... Got it. Now, why does one thing cool and the other thing warms?
Isn't it called like ocean breeze or like wind breeze or whatever?
Yeah, that's what we usually call it when you're like on the ocean, the cool air coming in from the ocean, right? The reason though is that when one thing warms, like if you put a hot object in your hand, is the object getting hotter while your hand's getting hotter? It's getting cooler, right? The reason your hand's getting hotter is because it's losing heat to your hand, isn't it? And so the same thing's happening here. When the ocean water cools, that means that the surrounding air is losing, it's gaining that heat from the ocean water, right? Yeah. Now, we could have done it the other way too. When the ocean water heats, that's going to be that cool breeze effect. Yeah. So it will be losing temperature from the air to the ocean water.
It's just like never seen my favorite part now.
Yeah, you gotta think of it more like if you think of it as paying, like payments, it works out better. So when you think of it a bit like if I get richer by $10, then somebody paid me $10, right? Yeah, somebody else had to have gotten poorer. Same thing happens with heat. So heat is neither created nor destroyed, and that means whenever something gets warmer, something else gets colder, right? And vice versa. Now, don't take that as an economics theory. Economics is more complicated than that, okay? Okay.
Oh, yeah.
No. Okay.
You should be our professor for that.
That would be interesting. When we know the specific heat of a substance, we can actually rearrange the specific heat expression, and this would actually give us that heat equation. Remember what I was talking about? Literally, a calorie definition is the specific heat of water. That's because they're actually the same equation, they're just rearranged. Okay? One leads into the other. And so we can calculate the heat lost or gained by a given mass of a substance over a certain temperature using that specific heat. And so what you would do is, again, the heat would equal the mass times the temperature change times the specific heat. You don't actually need to memorize this formula. The reason you don't have to memorize it is because the units. As long as you understand the units, you have the formula. So this right here, if we want to get into joules, what do we have to do to that? Multiply it by grams. That would get rid of the grams. That's mass, by the way. And then we'd have to multiply it by the change in temperature or degrees Celsius, wouldn't we? And that would get rid of the 2 units on the bottom, leaving us in the units on top. Okay? I'm going to share something that probably shouldn't be shared in this, which is that I was a absolutely terrible student. I would not study all the time. And then I would walk into the exams on chemistry for most of my undergraduate, and I would spend about 10 minutes taking all the different constants that they'd give me in the exam and deriving all the formulas. Because by giving you the constants, what am I actually giving you as well? The formula. Because the units of the constant have to be the units of the formula, right? Mm-hmm.
So the temperature change, the little triangle T, is the same thing as the Celsius?
Yep. Yep.
So like even when it says like the Celsius thing, it's still fine with like minus and
Yeah. Yeah, so this is the change in temperature. In these cases, the easiest way to sort of remember this is that it's a relative amount of energy. Or another way of thinking that is that, like, just because you changed going from one temperature to another versus the next shift up, that doesn't necessarily change the energy. Like going from $10 to $20 and then going to 20 to 30, that's not actually changing the amount of money I have to pay, right? That makes sense? And so I typically tend to think of these things like a grocery store. Yeah. Go ahead.
This isn't really important, but like isn't specific heat also abbreviated for C? Because I remember this.
Yes. Yes, you very much can abbreviate this for C. It tends to, it's this lowercase c usually. So they stopped using C around the time of the speed of light. Yeah, and so you can use C, by the way, but it gets confusing later on, especially for chemistry, because C is concentration as well. Lowercase c is the speed of light.
I thought the speed of light was FTL.
So what's Q?
No, FTL is faster than light, and is not actually something that can exist in the universe. But huh?
Wait, so if on that old formula,
Uh-huh.
what's Q?
Q's heat. Now Q is correct. That's still in use like that. That's actually the proper way of expressing heat. Yeah.
Yeah, we use that formula.
Mhm.
Q equals MC.
Yeah. Yep. Yep.
That-
Now was it C of S?
No, it was Q equals MC triangle T.
Okay. So it should technically be C of S. That is the proper designator for that. They don't use it in this textbook specifically because this is entry chemistry. That's non-majors course. And this right here looks close enough to that.
C of X.
That's for specific heat right there.
So like subscript S?
Yes. Yeah.
I thought specific heat was the Q.
No. Specific heat is the C of S, is specific heat. The heat is Q. So how fast the temperature changes is C of S or specific heat. The Q is the actual heat that's going.
So it should be Q equals MC of S.
You're rearranging, you're looking at two different ways of arranging the formula.
I am.
So you could do Q equals M, change in temperature, C of S. That right there is the formula you're talking about. Q equals mass times change of temperature times the specific heat or C of S. Yeah. Yeah. But you can also rearrange that the other way, which is the specific heat equation. Yeah. Yeah. So anyways, either way, as long as you have this constant or the units for it, you don't actually need the formula because you can just knock units off until you get what you want. If you want heat, that's joules, right? Okay, so let's use the heat equation to calculate the energy in kilojoules needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. You'll also need your plickers out at some point here, because I'll end up doing the plicker. Dun dun dun. Honestly, I'm mostly using this right now for these ones as an attendance record. Yeah, it's an attendance record. Yeah. Yeah, I don't even have the answers properly in here for these ones. Yeah. So, in the future, I actually have the questions in the plickers. But I couldn't change the 3 because I was midway through it with you guys and midway through it with another class.
Do you teach all those classes?
Yeah, these are all the classes I teach.
At one time?
Yeah, right now, this semester. Yeah.
Crazy. That's a lot.
Yeah, it's like below average for me.
You're just that good.
I've taught 36 credit hours one semester. 12 credit hours is sort of the normal average-ish, is between like 12 and 14.
You gotta give yourself a break, man.
Yeah.
So how many
Anyways.
classes do you teach
Is that
a day?
12 classes?
Not that many. Huh? 12 classes? Oh, yeah, 36 credit hours would be like 12 lectures. But a lot of those were labs as well, so it was more than that. Because the labs only count for like 1.5 to 2, depending on the university you're at.
You just only do chemistry, like that's your line of business?
Once everything's set up, that doesn't take as long as you think. The problem I'm struggling with is that I don't have any of my old setup stuff because I changed universities and I changed to Canvas and I changed to different books I hadn't been using.
Where were you before?
I was at Bethel University. And
Bethel.
before that, I was actually at like UMKC, KU, UCMO. It's Kansas City, Missouri area. And I taught at all 3 of those places at the same time.
You're allowed to not overwork yourself, dude.
Yeah, Bethel was my not overworking myself. It just didn't work out as not overworking myself.
Well, you don't have to overwork yourself at Cumberland either.
Oh no, this is not a bad teaching load.
How many credit hours are you teaching this semester?
Teaching load, that's 6, 9, and then 1, 2, 3 times 1.5. That would be 4.5. So that's like 13.5 versus 12. That's the normal. Yeah. It's not that bad. The number of loads is actually the one that kills you. If you teach like 6 different courses that are totally different, that gets to be crazy. Yeah, because deploying homework, takes time. Okay, so let's go ahead and solve the problem. So we're going to use the heat equation, right? In kilojoules, we need to heat 255 grams of copper from 24. How do we do this? Okay, so subtraction would be a good place to start because we're going to need that change in temperature, aren't we? So that sounds like a good idea. How do I get change in temperature? Yeah, 185 degrees Celsius minus 24. What is that?
161.
Very good. I heard that from a multitude of places. That's excellent. Okay. And so, what's my next part? Yeah, I need to multiply that, right, by 255 grams. Is there anything else I need to multiply? Specific heat. And that would have actually probably been the easiest place to start with this, by the way, because if you looked up the specific heat first, then you have the units, everything else needs to work out for. Okay? But this was always something you were going to need to do, so that was always a good idea. Yeah. These are all changes in temperatures anyway, right? So, just to change the temperature every time. It'll help you out. Okay? And so this is actually the specific heat of copper, if you look it up on that table. When I give you problems, I'm not going to expect you to have every specific heat memorized. That would be ridiculous. Nobody would spend the time doing that. And so you would have that value given to you, maybe on a table for multiple problems. And you would look that value up, and this is in joules, grams, degrees Celsius, right? So now what do I do with those numbers? So I have 255 grams times 161 degrees Celsius, and then what do I do? Okay, I want what? Kilojoules. Where's my joules in this problem? It's right there, right? Okay, I'm going to have to eventually convert it to kilojoules, sure. But this gets me into energy if I use that, right? So what I can do is take that joules number there, get rid of grams and degrees Celsius, right? How do I get rid of those numbers? Or those units, I should say. I multiply. Yeah, I need to multiply that specific heat by the change in temperature that I'll get rid of, degrees Celsius, right? I multiply it by the mass, that will get rid of the mass here. Okay? That would leave me in joules so far. Is joules what I want at the end of this problem? No, I need it in kilojoules. So I go ahead and do my conversion here, don't I? Okay? And I want B in kilojoules, so that's times 1 kilojoule, and that is related to 1,000 joules, right? Okay. Did I lose anybody in that? Please, if I did. Okay, maybe. Okay, let's go ahead and go back through this real quick, okay? Okay, so once I have the specific heat of this, okay? Okay, and I know I need that because I'm going to calculate the energy in kilojoules needed to heat. So I'm heating copper, okay? The specific heat is quite literally how quickly something heats, right? And how much energy is going to actually transfer to that in that process. And so I know I need that number. So I get the specific heat of copper. I write that down. Whoops. Let me rewrite that. 0.385 joules. That is per grams degrees Celsius. Okay. And so I have the specific heat of copper, right? And again, I'm just doing what do I have, what do I need, how do I get there? And so I need it in kilojoules. Well, it's joules right there, isn't it? Okay. So there's two ways you could go on this. Like any math problem, there's multiple directions you could go. I could get this in kilojoules. Does that make sense to you to do that now? Or should I just try to get the joules by themselves? Neither answer is wrong or right. Well, both answers are right.
I don't know what you're asking.
Okay. So if I want kilojoules at the end of this, I don't want divided by grams or degrees Celsius here, do I? At the end of this. This doesn't have a grams or degrees Celsius in there, does it? Okay? Meaning I have to get rid of grams or degrees Celsius somehow, right? And this is what I have so far. So I know I have to somehow get joules by themselves from that. I know I need to get that somehow into kilojoules, right? Okay. And so, which would we like to do first? Well, get into kilojoules? Sounds good. Let's get into kilojoules. Okay. And so I'm going to go into kilojoules. I divide it by joules, so joules will cancel, right? And there are how many joules in a kilojoule? 1,000. Got it. 1. Okay. Okay, so this leaves me with a kilojoules per grams degrees Celsius number. I can now see, well, I am going to get kilojoules out of this at some point, but I need to get rid of those grams degrees Celsius, don't I? Those aren't in my final thing I want. Okay? And so what do I have that's related to grams and degrees Celsius? I have grams of copper right here, don't I? Okay. How do I get rid of the grams on the bottom? These grams here. I multiply by those grams of copper right there, right? So I'm going to go 255 grams of copper. Okay. Grams will cancel. So now I have kilojoules over degrees Celsius that are remaining. Is that my answer yet? No, that doesn't have a degree Celsius on it, does it? Okay. And so now I need to get rid of my degrees Celsius, don't I? Okay. And so how do I get rid of the degrees Celsius? I plug in a change of temperature, don't I? Yeah. So my change of temperature is going to be 161 degrees Celsius. And again, degrees Celsius will cancel. And that will leave me with kilojoules only, right? Okay. All right. Okay, I'm not sure if this is a looking at me like, go on, Dr. Clausen, or looking at me like, I don't understand what just happened.
It's just not very
I
good what they're
understood
reading.
the first way better.
Okay.
Yeah,
And it's
it's
just like, it's just a lot.
The use of formulas?
Yeah, I like just filling in the, like, writing down each equals, I don't know, the same, and then I just fill in.
So that's fine. We can do the use of formulas in this course, and you'll be okay. Okay? I will warn you, though, in the future, trying to use formulaic response for everything, and I know that's how you've been taught to this point, and you haven't really experienced anything else, but that's actually setting up yourself to never be able to do any other complex math ever, or actual real-world math, because you'll never actually be able to do anything beyond that.
Why is it 1 over 1,000? Like, I get that they're the same, like they equal the same. But how do you decide whether or not?
Oh, it's canceling. It's literally because I needed to get rid of joules on the top here. So I put kilojoules first because I wanted that on top. And then I put joules on the bottom so I could cancel the joules on the top right here. Yeah. And so I then put in the number because that's how they're equivalent. That's the equality. Like it's 1 kilojoule for 1,000 joules.
You just make that a law. Literally, what you need on top is what you're trying to get. So
Mhm.
kilojoules is on top because you want to get to kilojoules. And literally, just remember that whichever one is bigger,
Whichever one you
Mhm.
need.
goes on top. And then
Yeah.
just know which one is bigger.
And whatever you're trying to cancel that was on top is on bottom. Okay. Did you have a question? I think you.
No, I figured it out.
Okay.
We were talking about that.
Oh, is it same thing?
Yeah, sort of.
Okay.
Thank you, though.
Hey, no problem. So yeah, it's you just put in units first in the position you want it to come out in. Yeah. Is there any other questions on this? Yeah. Again, feel free to use formulaic if you want to. Just remember you'll have to have all the formulas. So you'll have to write all those out. Okay? Okay. All right, so changes of state. So matter undergoes a change of state when it's converted from one state to another state at a constant temperature. Now, this is actually kind of a important part for definitions. It does this at a constant temperature. Okay? Does anybody ever seen chocolate melting? When you like melt down chocolate so you can make your own shapes of chocolate or chocolate glaze or whatever? Okay. How do they do that?
Yeah.
They just heat it up?
Mix it.
Okay. Do they do it over steam?
And you do it over water.
Yeah, you do it over water. You do it over heated water. Okay? If you just microwave it, you will actually burn some of the chocolate, and it won't come out the proper consistency. Yeah. If you try to directly bake it, it also will come out that way. And so what they do is you actually take a double boiler, it's what it's called. It's a pot at the bottom that has water, and the water is going to boil steam, and then that heats up the top container that has the chocolate. Okay? Same way you make bao. Anybody have bao? It's B-A-O. Yeah. 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 You can make dumplings, that sort of thing. Yeah. Anyways.
Do you bake?
Not so much. I do cook and bake those occasionally. Yeah.
That sounds like
They'll look the oven.
I'm actually pretty good at making like really weird dishes. Like
What's your favorite
other
one?
cultures'
What are
dishes.
some weird dishes you
Yeah.
make?
So, like, I make a lot of like Vietnamese and Thai dishes, and it's mostly stuff that you won't be able to get at a restaurant.
Just because Vietnamese is weird.
No, it's just because it's hard to find that stuff around here. Yeah. And I don't make the Vietnamese dishes I can get at a Vietnamese restaurant here. Does that make sense?
So when are you bringing them to class?
I don't even have most of my kitchen stuff here. Yeah. Mackenzie. I had to, basically, when I taught you guys, I came down on Thursday. I had no place to sleep.
Bro, why are you
Yeah.
telling me?
I literally saw and rented an apartment after I finished teaching you on that Friday.
Are you living in Lebanon?
I am now. Yeah. Yeah. So the matter undergoes a change of state again. So when we have for example, vapor, it can condense, and you've all seen condensation on your Coke cans or whatever, right? Okay, that's why it's called condensation, or rain is called condensation, right? And so vaporization is when you take that and you boil it, and it goes to a vapor state, right? Or gas state. Melting and freezing. Everybody understands melting and freezing, right? Fantastic. Now, let me ask you a question. When something is melting, is its temperature changing? No. Is heat flowing?
Yes.
Yes, most definitely. If you have an ice cube in your hand and it's melting, what is it doing to your hand? Making it colder. What's happening to the ice cube? Yes, it's having heat flow into it, and so it is warming, right? Got it. Okay.
So does that mean its temperature is changing if it's absorbing heat?
It is not. All that energy is getting used to melt it.
How is that not?
What about when you boil it?
Same thing. So when you make a boiling water bath, so let's say I take water and I boil it, that water is going to stay essentially 100 degrees Celsius the entire time until you run out of water. Okay? And the reason for that is all the energy is going to get taken up by taking these molecules here. See how they're all packed together and they're binded together? They're going to break them apart and split them up. Okay? And so that's where all that energy is going towards. Same thing for solid. See how they're really nicely aligned and you have all the connections made? When you melt something, all the energy from melting goes into breaking 20%-ish of the connections, and that gives you liquid. Okay?
Alright, so if it's getting colder, it's releasing heat.
Mhm.
And if it's getting hotter, it's absorbing heat.
You got it. Just like when I get poor, I'm paying.
You said when you get four?
Yeah, when I get poorer.
Don't wish that upon yourself.
It happens. So, again, melting and freezing. The melting is, while it changes from solid to a liquid, it's its melting point is that temperature that's going to do that change. Anybody know what the melting point for water is?
0 degrees Celsius.
0 degrees Celsius, 32 degrees Fahrenheit. You're both right. What is the freezing point?
0.
0 again, yeah. It's the same, right? So the freezing point and melting points are the exact same point, just like saying going in and out of the classroom is the exact same door. Okay?
If it's 0 degrees, will it be frozen or will it be water?
It'll be both. It will be at the point it's changing. So if it was all frozen before, some of it's melting.
Will it eventually all melt? Or will it?
No, it'll reach an equilibrium. It will go a little bit of each. Yeah. Okay, have you guys ever seen, have you guys ever been out on a cold day?
Yes.
Okay, and there's been snow on the ground?
In Tennessee, not really, but.
Yes.
A little bit.
Yeah. The last year,
It's the global cooling.
Yeah, I actually drove through that blizzard, by the way.
blizzard. There was not a blizzard here.
There was a blizzard.
There was a blizzard, yeah. But it was only for like one day. Yeah.
So if a temperature is constant, how can some of those be frozen and some of them not be?
What's happening is you have energy constantly going in and out of an object from the surroundings. Okay? So energy is constantly going to be exchanged. Some of these particles are going to get split apart and go over to liquid. Some of the particles in another place are going to get frozen together and are going to go in the solid. Think of it a bit like it's like a classroom when you guys aren't actually doing lecture, right? And so students are constantly getting up, and then they're sitting, and then they're talking to one person, and then they're not talking. And you can have both states existing, right?
But how does, I want to say, how does it decide what it wants to do, but like it's not like a
What happens is it's just an exchange function. So think of it a bit like if you were just throwing objects up into the air, right over a box. A certain number of them are going to fall into the box, right? Which ones fall into the box, that's another question, right? But you're going to get an overall state that will be achieved. The individual items can be different states, though, and are going to be constantly exchanging.
So is it just like different kinetic energy?
Yes, so once you're at, are we still talking about freezing and melting, or are we talking about when it's already at a state?
Like in between freezing and melting.
So when we're at the melting point or freezing point, yeah, your kinetic energy is still going to be moving around everywhere. Remember, these are not actually fixed in place objects. The atoms are constantly bouncing around and vibrating. And so some of them are going to pop off, and that's liquid. Okay? And some of them are going to accidentally reattach, and that's solid. Because what's actually happening in these things is it's in constant motion, and there's going to be spikes in this one area and lows in this other area. Okay? Yeah. And that's happening all the time. Like your bonds are constantly breaking and reforming. Yeah. Okay? And that's happening all around you all the time. The world around you is in chaotic motion all the time. We can't really show you that, especially on this level of course, because it just gets, notice all the words I had to use compared to this slide. It complicates the issue, right? But just remember, this right here, this is not frozen in place, right? These things are flying or all around you all the time, right? And they're bouncing everywhere, okay? Same thing here. These things are bouncing off each other like a very full pool table, okay? And they're just ding, 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 ding all over, right? Same thing here, they're just more tightly bound so they can't move around as much, right? And so if you have that average energy of that system high enough, you'll start breaking those bonds more, right? Did that make sense? Okay. It actually gets even weirder because like objects pop in and out of existence. Yeah. That's quantum. No, that's how the world works. You ever seen like a film? And it has the 60 frames per second? The universe works kind of like that. So things are just ding, 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 ding. Yeah. Anyways, it gets trippy. Okay, so this right here is a decent representation of this. Remember, heating it and cooling it, or melting and freezing something, is going to be a process that is reversible, and it can go back and forth all the time. Okay? And it does. It's constantly going back and forth. Things are slightly fluctuating all the time. Okay. The heat of fusion, this is going to be the energy that must be added to convert exactly 1 gram of a solid to a liquid at its melting point. So for H2O, that is going to be 80 calories or 334 joules of heat is needed to melt 1 gram of ice at its melting point, which is that 0 degrees Celsius. Now, that is the formula of this. You see solid going to liquid. Okay? Now, this right here is the heat of fusion represented as a ratio. Can everybody see that qualities are represented as ratios now? Okay. And we're all good with that stuff now? Yeah. You don't need to write down all of this, by the way. Yeah. And one of the things you can do for yourself so you don't have to write so much and you can pay more attention while you're in class is you can actually print these slides off as a note-taking format where it'll have little representations of the slides and then lines. Oh, you do usually black and white and grayscale? But, okay. They are, yeah. Home. Yeah, there's a link to them. Yep. No problem. Okay, so when calculating the heat needed to melt or when released from freezing water, we're going to use this equation right here. You notice that it's just the heat equation again, modified for this specific case, because we're not going to change temperature, right? So, for everybody that likes formulas, there's the formula, okay? Okay, so specifically, we're going to get calories out of this. We're going to use right here the heat of fusion, which is calories per gram. That's the heat of fusion for water. This right here then is the mass of the water. Note we will cancel off grams, leaving us in calories, okay? One of the ways you can help yourselves remember these formulas is this doesn't have any change in temperature. Okay? So as opposed to the specific heat formula, there is no change in temperature. Because when we are melting or freezing, the temperature is constant. Okay? All right. So, how many kilojoules are needed to melt 32.0 grams of ice at 0 degrees Celsius? Okay. What was the previous formula?
Heat equals mass times heat of fusion.
Okay, so we want heat, don't we? Okay. You all good with Q? No? Okay. Let's question mark kilojoules. Okay? We want kilojoules at the end of this, don't we? All right. And so what do we have? We have 32 grams of ice, right? Okay, and we have that we're at 0 degrees Celsius. We also have a constant that was given us in the previous slide. Does anybody remember that number?
80 calories.
Or 80 calories, yep. Was there one in joules?
333.
Very good. Okay, what was the number on the bottom, by the way? 1 gram of? Is over gram, right? Okay. So, we need to do two things to fix this problem, to have this solved. We need to take joules and we need to go into kilojoules. We also need to get rid of grams. Gotta get rid of grams, don't we? Okay. Okay. So, we go into kilojoules first. 334 joules over 1 gram. Okay. How do we get into kilojoules? Yeah, we put kilojoules on top, joules on the bottom, and there's 1,000 joules, right? Okay. And that will give us our number, which is 0.334 kilojoules per gram. Okay. Now, what's the next part of this? We need it just in kilojoules, right? Again, keep on track of what do I need. That number right there did not have grams in it, did it? So I'm not quite there yet. I need to get rid of grams. How do I cancel out grams? Multiply it by my number of grams, right? So I have 32 grams of ice there. Grams will cancel, leaving me in kilojoules. Okay. Okay. Now, in terms of formula, again, we need to write out your conversion factor. This is that same number we were talking about before, the specific heat, the heat of fusion here. And that's then going to be plugged in. If we use our formula, it would be mass times the heat of fusion right there, right? Times conversion factor to get into kilojoules. Okay? All right. Does anybody have any questions so far?
I don't know what to ask. I just don't understand.
Okay.
I don't think that like this is working for me.
The formula or the units?
Just like circling like
Okay.
what I'm doing. Because I don't know how we're getting from like one step to the next.
Okay. So again, what do I have? What do I need? How do I get there? Okay? Okay, so what do I have in this problem?
32 grams of ice.
Okay. Okay. So let's write out again. What do I have? $32 grams of ice, right? Okay. What else do I have? 0 degrees Celsius. And the last thing I have is... Okay, so let's look at the problem again. I need to melt, don't I? Okay. What's the process of melting? That's that heat of fusion. That's what that is. That's how much energy it takes to break apart those bonds and melt it. Okay? Another name for melting is fusion. Right? That's actually the same thing. Something's fusing. You guys ever seen ice cubes melt? They were separate objects. When they melt, they fuse together, right? Into one piece of water, right? Liquid. Okay. And so we need the heat of fusion, and that's 334, right? That's not a bad deal. Over 1 gram, right? You don't need to memorize it. In this case, I didn't give it to you again because it was given to you in the slide before. And it should just be like right up above in your notes. Okay. Okay, so that is again the heat of fusion. All right. And what told me I would need that is I need the energy to melt this. And this is happening at 0 degrees Celsius, which is the melting point, right? Okay. Okay. And so they told me in words that I need that. Okay. Now, did you guys memorize the formula, or do you want to use units? Yeah, I'll do units, and then we can do the formula on the other board. Okay? Okay. So unit-wise, what I would do here is I need, so where I want to end up on is a number of kilojoules, right? Okay. So I need to get into kilojoules. I have a number here that has joules. I choose that one literally because it had joules in it. Kilojoules has joules, this has joules. Okay? That's the only reason I did it, period. Okay, and so I go 334 joules, this over 1 gram. Okay, now I don't actually need to know a lot about this. All I need to do is just get rid of units until I'm in what I'm supposed to be in, right? And as long as every step of the way I use a relationship that is true, my end result will always work out, okay? It's just like, do I need to know how many steps there are in this staircase to get up the staircase? No, I just take one step at a time, right? Or maybe 2 steps for me. Okay, now, so I'm gonna need to do something to get rid of something here, right? So I need to get rid of grams, don't I? Let's get rid of grams. I have 32 grams of ice here.
Why are we getting rid of joules? Yeah, are we trying to change it to kilojoules?
We can, if you guys want to do kilojoules first. You can do it in any order because they're all multiplications, divisions. But yeah, let's do, you want joules? Okay. So I want to get out of joules and I want to get into kilojoules, don't I? Okay. And so how many joules again? 1,000. You got it. Sorry, I'm going back and forth and it's making me dizzy. Okay. I will definitely need to go to the clinic this week.
I don't think the bells are working because the internet's out, but we have like 30 seconds left.
Oh, wow. Okay. I guess we'll pick up from next time here. All right.
So I should go.
Yeah, wow. Okay. Okay, folks. Honestly speaking, once you get used to the units are the easier ones. Because you need to know less about the problem. The formulas is the harder way.